Swayam Prabha. Digital India. Educated India.
Okay, so good morning everyone. So last class we looked at the basics of circuit complexity. We saw the definition of what is a circuit, what we mean by the size of a circuit, and we saw some trivial upper bounds on the size of a circuit computing any arbitrary Boolean function. Okay. In particular, we saw this n into 2 to the power n upper bound, that any circuit will have computing a arbitrary Boolean function. So, what we are going to do today is we are going to look at some lower bound results, okay, on the size of a circuit as well as the size of a formula computing a Boolean function. Okay. In other words, what we will show is that if we take any arbitrary Boolean function, what is the smallest, I mean what is the least size of a circuit that can compute that Boolean function. Okay. If not for all, maybe for a large fraction of Boolean function, we will show that the size of the circuit is at least some value, or the size of a formula has at least some value. Okay. So, let me start by giving a definition. Okay. The C omega size of a Boolean function is the smallest sized circuit over omega that computes the function. Okay. Similarly, we can talk about the smallest sized formula as well. So, the L omega size of a Boolean function is the smallest sized formula, again over omega, that computes the function. Okay. So, yeah. So, now let us look at a theorem. So, the first theorem that we are going to study today was given by Shannon. So, this is also called Shannon. Shannon has many theorems. This is one of his very famous theorems in circuit complexity. So, what he showed is that most circuits or most functions over n variable, so most n array functions, okay, have C beta 2 that is greater than size at least 2 to the power n over n for sufficiently large n. Okay. Okay. So, what do I mean by this? So, what we mean is that, so we will show that a very large fraction of Boolean functions over n variables require circuits of size at least this much. Okay. So, for very large class of Boolean function, there are no circuits which have size smaller than this quantity. Okay. And as you can see, this is a exponential quantity. Okay. For sufficiently large n. Okay. So, maybe for small values of n, things can be small, but as n tends to infinity, this bound is achieved, this lower bound is achieved. So, how do we prove this argument? So, before I get into the proof, let me just give some overview or some idea how we will proceed. So, what we will try to do in these kind of results, okay, is we will try to compute how many circuits. So, suppose if I fix n, okay, as the size of the input which is there, and I fix a size s. So, let us say I want to count how many circuits are there of size s over an input of size n. So, I will try to estimate a count for this. Of course, we do not require an exact count, we will just get an upper bound on this count, and then we will compare it with the total number of Boolean functions over n variables. How many functions are there over n variables? How many Boolean functions are there? Yeah, we saw this last time, it is 2 to the power 2 to the power n. Okay. We will compare these two quantities and that will give us this result. Okay. So, that is the standard procedure we will follow. First, we will look at this result for circuits and then we will look at the result over for formula as well. Okay. So, let f s of n be the number of Boolean circuits over B2, number of, let me just say it over here, n array Boolean circuits over B2 of size s. So, we will try to get an estimate on this quantity Fsn. Okay. So, how do we get an estimate on this quantity? So, first of all, look at a circuit. Okay. So, this circuit will have s gates. Okay. Now, each of these gates is an element from B2. How many elements does B2 has? No. B2 is basically all gates with 2 inputs. So, it is 2 to the power 2 to the power 2, which is 16 gates. Okay. It can be anything, it can be any of those 16 gates. Okay. So, the De Morgan basis has 3 gates, and or and not. Okay. So, this is the B2 basis we saw last time. So, okay. So, each of these gates can be one element from B2. Okay. Now, it is a circuit, which means it is a directed acyclic graph. So, each gate, so totally how many nodes are there in the directed acyclic graph? How much? How many gates are there? S gates. How many input gates are there? N. So, what is the total number of nodes in this circuit? So, it is n plus s, right. So, all the input gates or all the input variables plus all the non-input gates. Okay. So, it is n plus s. Now, fix a gate. Okay. Let us take any particular gate. So, from how many gates can it take input from? Okay. So, it can take its each gate has 2 input wires coming to it, and each of those input wires can come from any of the other n plus s minus 1 many nodes in this circuit, right. So, the total choices or the total number of choices for inputs to a fixed gate is n plus s minus 1. Anything else? I am not talking about the input gates, I am talking about the other gates. Okay, these s many gates. So, I have s many gates. So, each of those s gates can take its input from any of these n plus s minus 1 many gates. Okay. And there are two inputs to a particular gate. So, this will be n plus s minus 1 whole square. Yes, this can be anything from B2. I am only looking at the input to these gates right now. Okay. Now, this can be any element of B2. B2 has 16 element. Okay. So, which means that the yes square means that. So, suppose if I have a gate, okay, let us look at a gate. Okay, let us look at a pictorial view of this. Okay. So, I have some gate, okay, let us call this as G. Okay. First of all, G is an element of B2 and G takes input from two other gates, G1 and some G2. So, for G1 there are this many choices, for G2 there are this many choices. So, therefore, the total number of choices for G is this square. Okay. Now, how many choices are there for this G itself? 16 many choices, because B2 has 16 elements. So, therefore, for the gate G, we have 16 n plus s minus 1 whole square possibilities. Okay. So, this is for a single gate. No, so G can be any of the 16 gates. Okay, so this G can be any of the 16 gates that are present in B2. So, there are 16 choices for G, there are n plus 1 minus 1 choices for G1 and there are n plus s minus 1 choices for G2. Yes. Okay. Now, so this is for one particular gate, right. Now, the point is that I have a total of s many gates. Okay. So, so before I write that total, okay. So, therefore, the number of possibilities for a circuit of size s over n variables is, so each of the gates. So, now I have s many gates, each of the gate can be one of these possibilities. So, it will be 16 n plus s minus 1 whole square whole to the power s. Okay. Now, here actually we are doing a very gross over counting, because we are also counting, we are also looking at, so let us say if I have, suppose if I have let us say 3 gates G1, G2, G3, okay, So, G1, G2, looking at a circuit which has this G1, G2, G3 and G2, G3, G1 are basically the same. So, basically I am not considering, so basically I am looking at ordered tuples of gates over here, which is not required. Okay. So, what I need to look at is unordered tuple. So, I will divide it by s factorial. Okay. So, this is because the ordering of the gates does not matter. Okay. So, whatever order I write the gates in, it is basically I am looking at the same circuit. So, this is the total number of possibilities for FSN. Okay. So, my F S of n is upper bound. So, again as I said that this is just an estimate, this is an upper bound is 16 n plus s minus 1 whole square whole to the power s divided by s factorial, right. Again, so basically the way I am counting circuit is is I am looking it as a DAG and I am trying to count all DAGs which has a certain structure and how many such DAGs are there, right. Now, it can very well be possible that some of those DAGs even do not represent a circuit, that can be possible. I do not care about it because I just need a upper bound in this case. Okay. So, now let us try to simplify this quantity over here. So, first I will use Stirling's approximation for s factorial. So, I can write it as 16 to the power s plus n minus 1 whole to the power 2s divided by s to the power s divided by. So, Stirling's approximation is s factorial is greater than or equal to s to the power s divided by 2 to the power s or e to the power s, I think. Yeah, e to the power s. E to the power s. So, this I can write as 16 e whole to the power s. So, I will take this s outside. So, this becomes s to the power 2s 1 plus n minus 1 over s by 2s divided by s to the power s. So, this 2s and s cancels out. So, we get s to the power s over here. So, what we have here is okay. So, before let me just say something. So, this quantity, so can you give a bound, upper bound on this quantity 1 plus n minus 1 over s? Huh? So, what can we say about n minus 1 over s? Huh? I am sorry? Which one? S is bigger than n. Let us, yeah. So, n minus 1 over s is at least less than 1, that is all. Okay. So, this quantity is upper bounded by 2. Okay. So, I will just keep that as the bound. So, what I get is, so 2 to the power 2s is 4 to the power s. So, this becomes 64 e to the power s. So, I mean we cannot say it is half or anything. I mean n can be, let us say n can be n minus 1 by s can also be like 0.9. We can't say it is half. So, okay. So, it can be anything, but we know that it is at least or it is at most 1, it cannot be more than 1. Okay. And now, this is s to the power s. Okay. So, this is a constant 64 e. So, this is actually this is equal over here. Oh no, this is less than or equal to. So, this is equal to c to the power s times s to the power s for some constant c. Okay. Now, we have this quantity over here. So, we will now take a value for S. Okay. Now, so let us say we set S to be 2 to the power n. So, what is the bound that we wanted? We wanted 2 to the power n by n. So, let us set S to be 2 to the power n over n. So, S was an arbitrary variable for us. We can set it to any quantity that we like. So, we will set S as this, and now let us see what this quantity becomes. So, f s of n is c to the power 2 to the power n over n times 2 to the power n by n whole to the power 2 to the power n by n. Okay. So, this would, how can we write this? So, this becomes equal to c by n. So, I take this n outside. So, c by n 2 to the power n by n, and this is times 2 to the power n times 2 to the power n by n. So, this n and n cancels out. So, we get c by n 2 to the power n by n times 2 to the power n. Okay. So, what can we now say about this quantity on the left hand side? Any guesses? C is a constant, n is a arbitrary quantity. In fact, we assume n to be sufficiently large. So, what can we say about this? It is a small number. In particular, this quantity is less than 1. We can assume that for sufficiently large n, this is less than 1, and if this is less than 1, what can we say about this? This tends to 0. So, as n tends to infinity, this quantity tends to 0, and what is this? This is the total number of Boolean functions over n variable. So, we can write this as small o of 2 to the power n. So, what is small o notation? So, again, for those of you who are not familiar, small o means that this quantity is asymptotically smaller than 2 to the power n. Okay. So, therefore, actually the proof is over now. Therefore, for most Boolean functions, we require circuit of size greater than or equal to 2 to the power n over n, because this was the number of circuits which is much smaller than, asymptotically smaller than the total number of Boolean functions. So, therefore, for all remaining Boolean functions, we require circuits of size greater than S. So, any questions? We say a circuit. Yes. Yes. Overall. N-ary means that the circuit has n inputs. The circuit is over B2, which means that each gate is an element of B2, which means that each gate has a fan in, or each gate takes 2 inputs. Okay. So, I do not think I formally used the word fan in last class. So, fan in of a gate means the number of inputs to that gate. Fan out of a gate means the number of outputs from that gate. So, the moment we say that the circuit is over B2, it means that the fan in of every gate is at most 2. Okay. Any other questions? Yes. Think of the DAG, the directed acyclic graph. So, what we said last class is that a circuit is a DAG. So, think of that DAG, how many nodes are there in that DAG? Okay. That is what we are referring to over here when we say n plus s here. Okay. Anything, yeah.
Sir, the quantity 2 to the n by n, we can put any constant in the denominator. 2 to the n by cn.
You can put, yeah.
Then this will work. But we cannot put n square, no? 2 to the n by n square.
No, no. So, I want to put a quantity which will simplify to something that I can work with. You can put anything for s, okay, but I want to put a quantity that would simplify and give me a asymptotic quantity like this.
Factor of 2 to the n there.
Yeah. You can put anything for s, nobody cares, but I want to put something which would simplify and give me a quantity like this, where it is 2 to the power n multiplied with some quantity that tends to 0.